topics. Continuity and differentiability is an important starting step to learning calculus, right? There's more beyond this topic, but this is important to understand. And what we are going to do today is look at what is continuity, how do we check if a function is continuous, what is this concept of derivative, how do we calculate the derivative of a function, with some simple examples. And towards the end, we'll also learn about what is the differentiability of a function and how do we check if a function is differentiable. Right? These are just some of the basic things. And these things are also taught in the, I think, in the 11th standard or in the 12th standard. In CBSE, it is in the 12th standard in India. But in all over the world in various curriculum, this is taught somewhere in the 11th or the 12th standard. And because some of the, or probably many students don't understand the basics, they may find it a little difficult to grasp and even solve problems. So that's what we'll focus on. Okay, so let's start with continuity. Look at this diagram here that's shown to you. So Sunil, is this diagram, is the slide and diagram visible? Just to check.
Yes, Rahul.
Yes.
Yes, Rahul. Go ahead.
Okay. So friends, in between, sometimes I'll just keep checking with you if you are following me, and if you have any comments, you write in the chat message, and I hope it's okay that we'll take up your questions at the end of my presentation, right? And even after this session, we will have time to interact in Google Classroom or some mechanism we'll set up, and we will interact. Okay, so look at these 6 diagrams drawn here. Look at the first. Look at the top left one, right? This one here, and it's a straight line, right? So how do we check whether it's a continuous function? So let's take a random point C on the x-axis. So the first condition, a simple visual check. So let me first talk about a visual check. To test whether function is continuous, if the mathematical expression is simple, you can draw a diagram. You draw a curve like this, right, in a graph. So if you can do that, then you can simply see if you can trace the curve without lifting your pen or pencil, right? Can you do that? That's a simple visual check first, right? To know whether a function is continuous. So at whatever points or over whatever interval you can do so, it is continuous, right? That's the first thing. So look at this second function here on the top, right? We can even trace that, right, without lifting our pen or pencil. So even that is continuous, seems to be continuous. Look at this top right function. It takes a sharp bend here at this point, but still we don't have to lift the pencil, right, or the pen. We can still trace it, right? Now look at this bottom left function here. Now this function, it is not, you see that it is not defined. I don't know if it is clear enough in your screen, but the way this curve is made, and what's written here, it's not defined at x equal to c. Okay, so and everywhere else it is defined on the x axis. So if you try to trace it, you go up to here and then you will have to lift your pen, right, to proceed further, and that's an indication that it is probably not continuous at x equal to c, right? So look at this other function here, the bottom middle function. Now this function, as this explanation suggests, it is defined at all values of x, but it takes one value for x less than c, and it takes another value for values of x greater than equal to c, right? So so if you start tracing it, you will have to again stop here and then lift your pen and then start and then proceed further, right? So that's another indication that it is not continuous. Look at this last function here, which is again defined at all values of x, but it takes a different value at x equal to c, right? It's indicated by a point here, than all the values that it takes at the other values of x. So if you start tracing it, you will have to again stop here for a while, lift your pen, then and then maybe mark this point and then proceed further. Again, indicating that it is probably not continuous. So how do we define it more concretely? So the first part of the definition is, let me rub this off. The first, yeah, Sunil.
Rahul, if you can go a little slower, I think some of them are updating on the chat. they cannot hear your voice.
Oh, I see.
See whether you can speak into your mic and little slowly.
Okay. Okay. I will. So thanks for the feedback, friends. I will try to speak a little slow. So is my voice clear now? Is this okay? Sunil,
It's fine
Devashish,
now.
others.
Yes,
Okay.
it's
Okay.
fine.
Fine.
It's
Fine.
better.
Fine. That is fine. Okay. So so. So I will continue. I will not repeat what I have said. I hope that's okay. What I have said, the summary of that is that if you can draw the figure of a particular function on the graph, then the first visual check is whether you can trace it. You can trace it without lifting your pen or pencil, right? So the entire interval over which you can trace it, the function is continuous in that interval, right? So that's the thing that I said until now, right? And we saw that you can do so for the top three diagrams that are shown here, and you can't do so for the bottom three curves, right? Uh, Now we'll look at more precise definition, right? So there are two parts to testing whether a function is continuous at a point, let us say x equal to c. First is that the function should be defined there, right? So check whether the function is defined at point x equal to c, which means whether it has a value, it has a unique value at x equal to c, right? Um, so that's the first condition. So we see that this function is defined, the first one out here. The second one is also defined at x equal to c. It also takes a value at particular value there. The third one is also defined at x equal to c. This one is not defined on the bottom left, right? We see that there's a hole here. And as this one says, this function doesn't exist at x equal to c, right? So this one is not defined. Let's put a cross there, right? How about the bottom middle function? This is defined. It takes a value at x equal to c, right? Which is somewhere here. How about this last function? That is also defined at x equal to c. It takes a particular value, which is somewhere here, right? So five of these are defined. The second condition from the tracing line, tracing the curve test that we discussed. The second condition you would probably appreciate is that the function should approach the same value whether you approach it from the left hand side or from the right hand side. Okay, so let me use another color to show. So what we are saying is that you look at the point where you want to test for continuity. So let's say x equal to c here, and you try to approach x equal to c from the left hand side on the x-axis and from the right hand side, right? You go to the values closer to c from the left hand side and the right hand side, and look at what are the values that the function, what is the value that the function takes as you approach x equal to c from the left side, and what is the value that the function takes as you approach x equal to c from the right side, right? And here we see visually that it converges, the function value converges to the same point, right? Whether you do from the left or from the right, and it converges to the same value that it takes at x equal to c, right? So this is the second condition, right? So you look at this other function here, the second function here. If we approach x equal to c from the left side, we see that the function value approaches this point. If you approach x equal to c from the right side, you again see that the function approaches the same value, and this happens to be the value that it has at x equal to c, right? So that again, that is again an indication of continuity. Look at this third function on the right. So as you approach x equal to c from the left side, the function approaches this value. As you approach x equal to c from the right side, the function approaches the same value, and which also happens to be the value that it takes at x equal to c, right? Now this bottom right function, it is not even defined at x equal to c, right? So there's no question of continuity, because no, it's not, it doesn't have any value there. What about this function here on the bottom middle? As you approach x equal to c from the left side, you see here that you approach the function from here, right? And the value this function takes for values of x very close to c and to the left of c is basically this value somewhere here, right? And if you approach x equal to c from the right side, right? So think of values of x closer to c but slightly greater than c. Then you see that the function takes takes this value, right? You approach it, it takes this value, and this is not equal to the previous value. So what we say is here is that the limit of the function as x approaches c does not exist, because the left hand limit LHL is not equal to the right hand limit, right? So it's not continuous. even though it has a value at x equal to c, right? Look at this last function, right? Here, as we approach c from the left side, the function takes approaches some value, which is this one. If you approach c from the right hand side, the function approaches the same value, the same value. So interestingly, here the limit exists. Since LHL equal to RHL, the limit of the function exists, but it is not equal to this the value that the function takes at x equal to c. That value is different. That's somewhere here, right? So this is an interesting case where the function is defined at x equal to c. It also has a limit at x equal to c, which means that the function value approaches the same number if you approach x equal to c from the left and the right hand side. But the two are not same. The limit of the function as x approaches c is not the same as the value of the function at x equal to c. So this is what how we define the continuity. I hope you appreciate it from these diagrams. So for f, a function f or fx to be continuous at x equal to c, first thing is that c must be in its domain, right? So which means that fc must be defined. It should take a value, an arbitrary value k, right? And the second condition is that the limit of the function as x approaches c should also exist, and it should have the same value that the function takes at x equal to c. These two should be same, right? And another way of saying the limit condition is that the limit of the function as you approach c from the right hand side, we denote it by this expression, limit of fx as x approaches c plus, right? So plus means values on x slightly greater than c, right? So you approach it xc from the right hand side should be equal to the limit of the function as x approaches c minus, which means you approach c from the left hand side. Think of values of x very close to c but slightly smaller than c. So these two should take the same value, and that value should be equal to k, the value that the function takes at x equal to c. This is a simple condition for continuity. And let us now move further. And
Rahul, one
yes,
request from a participant. Can you
yes,
just repeat that last point when you are defining that equation? Just go
yes,
back to the
yes,
previous
yes.
slide.
Sure, 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 sure. So let me rub this off. Yeah, okay.
Yeah,
Uh,
yeah, from here.
yeah, yeah, sure, sure. Uh, so I hope this part is clear. The first condition is simple. The function has to be defined at x equal to c. We are testing its continuity at x equal to c, right? So it should be defined, which means c should be part of its domain, right? Which basically means that function should take a unique value at x equal to c, right? That's the first condition. The second condition is that as you approach c, if you think of values on x very close to c, uh, uh, that's what we write as limit of function as x tends to c, right? This means what is the value that function takes as you approach c, right? As you take values, think of values on x very close to c. So that should be the same as the value of the function at x equal to c, right? And which is what we see happening in the top three functions here, right? And which is what we see doesn't happen here in the bottom function, right? The last one that we saw, and even the middle one on the bottom, right? This one here is not even defined at x equal to c. The first condition is violated. But look at the bottom middle and the bottom right function. So in these two functions, the first condition holds, but the second one is violated, right? And what do we mean when we say the limit should exist? Basically, that the limit from the right hand side and from the left hand side should have the same value. That is what we mean by the fact that the limit of the function exists at x equal to c, right? So you say limit as x tends to c plus. What it means is, as you approach x equal to c on the x-axis from the right side, right? So think of values on x on the x-axis very close to c, but slightly larger than c, right? So that's what we say here. Look at this last diagram here. As you approach c from the right side, so think of values of x slightly more than c, but very close to c. And look at the value that the function seems to be taking, right? The function is coming from here, so it's taking somewhere here, this kind of a value. And that should be same as the limit of the function as x approaches c from the left hand side. That's what we write as x tending to c minus, right? From the left hand side, from this side. And you see here that the function seems to be approaching the same value here in this bottom right curve, right? So the limit exists, right? But the problem is that in the last diagram, this is not equal to k, right? This is not equal to k, because what is k? K here is the value somewhere here. In this diagram, I'm sorry, I've probably overwritten too much. It may not be very clear, but basically the function here takes another value at x equal to c. So even though the limit exists and the function is defined at x equal to c, but the two are not equal, and therefore it is not continuous. I hope that is okay. Okay, so let's move on. So let's test more rigorously, right, using our definition, whether these functions are continuous or not, right? So look at this left one here first, right? So this is a function which has this expression here, x modulus, which basically means that we can write it as having the expression minus x for x less than 0 and plus x for x greater than equal to 0, right? And we draw it like this curve. Now, let us see what happens here. Uh, Now, is it defined at x equal to 0? Yeah, obviously it is defined. We see that at x equal to 0, it takes the value expression x. So therefore, you substitute 0, you get a value of 0, right? What about the left-hand limit? Does it have a limit from the left-hand side? So what it means is, as you approach x from the x is equal to 0 from the left-hand side, we are testing whether it is continuous or not at x equal to 0 right now, right? So keep that in mind. So as you approach x equal to 0 from the left-hand side, what is the limit of the function? So look at this one here. So think of values on x-axis slightly smaller than 0, right? So which means we're talking about small negative values. And what is the expression of the function for the small negative values? It is minus x, right? So we are essentially talking about the limit of minus x at x tends to 0. That is the left-hand limit. And you can simply substitute x equal to 0 here, and you get a limit of 0, right? And now let us look at the right hand limit, right? So what happens here, uh, as you approach x from the right hand side? So think of values of x slightly greater than 0. And what is the expression that the function takes for small positive values of x? Well, that is x, right? It takes the expression of x for any value of x greater than equal to 0, right? So that is x. And therefore, we again substitute and get a value of 0. So what we see here is that the limit exists, its value is 0, which is same as the value that the function takes at x equal to 0, and therefore it is continuous, right? So a simple test. We could see that visually, but we could also confirm it through this method. So at x equal to 0, the function is continuous. That's what we've shown. What about other points? What about other points in its domain? Other points, you don't even have to check this rigorously, because for values of x which are positive, so look at the values here. For example, for any value of x that is positive here on this left diagram, the function is a smooth line, right? So you don't have to even do this kind of a rigorous check here, right? It's obviously continuous. And for any value of x that is negative, right? So think of values here. Again, function is a smooth curve. Here it happens to be a straight line. But even if it were not a straight line, a smooth non-linear curve, you could confidently say that it is continuous. So therefore, what we are saying is you have to be particularly careful about these sharp bends or breaks. That's where you need to rigorously check whether a function is continuous or not, right? At any other point in its domain, for example, in this case, for positive values of x, for negative values of x, where the function has a smooth expression, either you can see that from the curve or from the mathematical expression here. It's not necessary to check in a rigorous way. Without that, you can say that it is continuous, right? So let's look at this other example now. We will move to the next one now here. So let's look at this second one here, right? So second one is pretty simple. So look at this expression here. It may not be so clear from this diagram, But second one is not defined at x equal to 0, right? Its domain contains all real numbers on the x-axis except 0, right? And we have shown that in this diagram by a little hole here. So what we said was that this second function here is not even defined at x equal to 0, and it is shown by this small hole here in this curve, right? So there's no question about its continuity, right? It doesn't have a value at x equal to 0. 0 is not part of its domain. That's what we say. And therefore, it is not continuous. So that's a pretty straightforward thing. And let's now move on to the third function, right? Which if you look at it from this mathematical expression, it is defined at all values of x. But for x less than 0, it takes an expression minus x. For x equal to 0, it takes a value of 1. And for positive values of x, it takes an expression of x, right? So at x equal to 0, it takes a value 1, right? And here, although you can check visually that it is not continuous, but we can also check from the method that we just introduced. It takes a value of 1 at x equal to 0. And if you look at the limit of the function from the left hand side, you see that it takes a value of 0, right? Because you think of values of x which are close to 0, but very slightly smaller than 0, which means very small negative values. So it takes expression of minus x, and the limit of that at x tends to 0 becomes 0, right? And the right hand limit also becomes 0 because it takes an expression x for small positive values of x. And even though the limit exists, the value of the limit as x tends to 0 is 0, which is not same as the value of the function at x equal to 0, which is 1. So therefore, it is not continuous. So what we say here is, interestingly, that uh, the function is continuous at all points in its domain except at x equal to 0, right? So x equal to 0 is part of the domain of the function, but it is not continuous there. Okay, so there is a example that I'll leave you with. I'll not solve this one because we have limited time. But the only point so if you can see this example, right? This function fx, which takes these different expressions in these three intervals. So the first interval here is x greater than 0 and less than pi by 2. It takes this expression. The second interval it's a point, actually, not an interval, x equal to pi by 2. It takes a value 1 by 2 there. And the third interval is x greater than pi by 2. And it takes a different expression here, right? So these expressions look a little complicated. It might be difficult for you to draw a figure, right? So what do you do in this case? So the simple thing is, uh, 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 always remember, and it must be easy to convince yourself that certain kind of functions are continuous in their domain, uh, uh, right? And what are those obviously continuous mathematical functions? For example, any polynomial function is continuous, right? So for example, 3x is continuous, 4x square is continuous, right? Even the sum of two polynomial terms is continuous. So 4x square plus 3x minus 6x cube plus 10 would be continuous, right? Because if you draw their figure, you will see that it's a smooth curve, right? And if a function is not defined at a point, right, then that point is not part of the domain. So you don't even have to check for its continuity, right? It's not obviously continuous there. But these functions are defined in their in the over the entire real axis, and they are continuous. The trigonometric functions are continuous in their domain. For example, sine x is continuous for all real values of x, right? How about tan x? Tan x, is continuous in its domain. So, for example, if you draw the diagram of tan x, it might look something like this, right? So it's not defined at certain points, but the points where it is defined, it is continuous. So, for example, tan x would not be defined at x equal to pi by 2, right? So this might be pi by 2, and tan x is not defined there, right? But so pi by 2 is not part of the domain of tan x. but in its domain it is continuous. So so therefore what we can say here is that this function here, 1 minus sine cube x by 3 cos square x, would be continuous at all points except the points that are not in its domain. So you all that you need to check for is that in this interval, is there any point where it is not defined? So look at the denominator. If the denominator takes a value 0 at any point in this interval, that's the only point where it is not defined. Otherwise, it would be continuous at other points. And just taking this as an example, you see here that cos square x takes a value of 0 or at pi by 2 and 3 pi by 2 and so on, right? So in this interval, x between 0 and pi by 2, where pi by 2 is not part of the interval, it is defined. So this function therefore would be continuous in this interval, right? So the point I'm making is that individually in these three intervals, uh, these uh, these three expressions are continuous individually in their respective intervals, right? So all that therefore you need to check for is the the point pi by 2, right? Whether it is continuous at pi by 2. That's all that you need to check in a rigorous manner, because it takes different expressions at pi by 2 and at values slightly less than pi by 2, right? And at values slightly more than pi by 2. So you need to find the left hand limit and the right hand limit. Okay. Now, just to conclude this continuity topic, if two functions f and x are continuous, right, then their sum will be continuous. That must be intuitive to you, right? So f plus g would be continuous, f minus g would be continuous, a product of those two functions would be continuous. So, for example, you can think of 3x square as product of 3 into x, right? Individually, these three are continuous functions, and therefore their product is continuous. Or you could think of the product of sine x and cos x, right? Both of them are continuous and have the same domain. So in that domain, the product would also be continuous. So the quotient of two functions, quotient of two continuous functions, f divided by g, would be continuous except at points where g is not defined. So at x equal to c, if g is not equal to 0, then it is continuous at x equal to c. Same holds the case with 1 by g. Constant k multiplied by a function is continuous. So we saw that here as well. This constant c3 multiplied by a continuous function is continuous. The negative is continuous, and the composite of two functions is continuous. F of g, right? So let's look at a simple example there. So think of a function, let's say sine x square. Okay, so you could think of this as f of g, right? Where gx could be written as x square, okay, and f of g could be written as sine g, right? So therefore, f of g is sine g, which is sine of x square, right? And we know already that x square is a continuous function and sine g is a continuous function. So therefore, sine x square would be a continuous function, right? So, so that's where we end this topic.